Okay, welcome to Chapter 9. This is for the most part, the end of the quantitative chunk of the course, which will be sad for some of you, happy for others, I'm sure. So we're talking about statistical inferences here, and the basic idea is that we have some population of interest, but it wouldn't be feasible to collect data on everyone, and so we take a small sample, hopefully a random sample if we want to get that external validity, but often that's not practical, so we get some kind of sample, do some kind of test, analysis, and at the end then whatever results we get for the sample, we extend to the population. So, again, we're trying to draw accurate conclusions about what some kind of effect will be in a population, but there's the internal and external validity concerns that we do have to be worried about. And by the way, I haven't mentioned this much. There's very, very few studies that would have high external validity and high internal validity. To have a random sample and a random assignment to control for all types of measurement error and all other threats, I maybe have seen a couple in my lifetime, but that's typically not the goal of a single research study. A single research study will try to get some kind of either strong external or strong internal, and then it has to be combined with other research studies to create a solid message. So in these inferential studies, we have sampling errors, which means our sample may not represent the overall population, which you could see would be an issue for external validity, and measurement errors, different types of validity or reliability that were described in Chapter 8. So when we talk about the null hypothesis, we're saying that there's nothing going on. Null is nothing. No differences between the males and the females. No differences between the people who were given the medicine and people who were not given the medicine. No relationship between height and weight, or whatever. We might be looking for a correlation there. So a null hypothesis means that nothing is going on, no difference between the groups. Typically a researcher will not want the null hypothesis to be true because they're trying to show that there is some effect or is some relationship going on. So they're going to conduct a test. They have a level of significance that they choose before they do the test, and that's important. This level of significance, or alpha level, has to be chosen before the study is conducted, before the data is collected anyway. It's going to say how much of a type 1 error are we willing to get. Oftentimes this is a 5%, so a 0.05 alpha level is very common in educational research. Medical research, it often is a little bit smaller because we don't want to make a type 1 error, and we'll talk about type 1 in just a second. So the level of significance is you're setting how much of an error are you willing to accept, type 1 error. Now type 1 versus type 2 error, so you conduct the study, you get a p-value, which we'll talk about in just a second. If the p-value is less than your significance level, then you're going to reject the null hypothesis. You're going to say the treatment's effective, or there is a difference, there is a significant difference between males and females, or between elementary and middle school, or between people who were tutored and people who were not tutored with this certain method. So a type 1 error is danger there because you rejected the null. You said there is not a difference, or there is a difference, sorry. There is a difference when there really wasn't. Okay? So a type 1 error can only happen if you say that we reject the null, we say there is a difference, because of this treatment, this drug, this intervention, there is a difference, but you're not correct. That would be a type 1 error. Type 2 error would be the opposite. Well, we weren't able to reject the null hypothesis. We weren't able to conclude there's any difference. We weren't able to conclude this treatment is effective, this medicine is effective, when really the treatment is effective or the medicine is effective. So type 2 error is when you should have rejected the null but didn't. Type 1 error, you rejected it, but you shouldn't have. So this statistical significance then, this p-value, this probability of getting results that you did in your sample, or even more extreme, further away from the null hypothesis, if the null hypothesis is actually true. Now you might think, if the null hypothesis is true, why would you get a sample that would suggest that the null hypothesis isn't true? Why would you ever reject the null if it really is true? The problem is, even if the null hypothesis is true in an overall population, I'm going to be very general, and I hope this isn't coming across as sexist. Let's say that men and women really are just as good at sports overall, in the overall population. But now we get a sample and we look at 5 professional baseball players, major league male baseball players, and we look at 5 females just randomly sampled from the population. In this case, the male baseball players certainly will have a higher performance, assuming the outcome is some baseball indicator, than the females. So if we then say, okay, well, males are better at baseball than females, that would be a type 1 error, assuming that males and females are equal in the population. So it is very important to recognize that there's always a chance that your sample doesn't accurately represent the population. Okay, now what happens if your p-value is higher than your significance? So you had an alpha of 0.05, but in your specific sample you got a 0.07. Does that mean that the null hypothesis is true? No, not necessarily, but it means we don't have really strong evidence to kick it out. It's not far enough away, our sample results are not far enough away from what we would have expected with the null that we can be confident, at least with 95% confidence, that that the two groups really are different, or the treatment really is different than the not treatment. Okay, so instead of that, we just fail to reject the null hypothesis. Instead of accepting it, we just say there wasn't enough evidence to reject it. There's always a chance, no matter what you decide, you could always make an error. This is the difference between statistics and much of mathematics, where there's certainty. Statistics, it's all about probability that, yeah, we are pretty sure that this is correct. So if you reject the null, you could have made a type 1 error. If you don't reject the null, you could have made a type 2 error. No matter what happens, you could have made an error. And the reality is, you probably never will know. And one thing that I want to mention, sample size does affect your statistical significance. You can buy statistical significance. What I mean is, by a higher sample size, everything else equal, the more chance you will have of rejecting the null hypothesis, which sounds weird, but it's because we have a tighter level of accuracy that there is some effect going on. It does not mean that the effect size is larger, which is important. So effect size is often this Cohen's d, or the r squared if we're talking correlations. And the effect size, now this one says 0.3. I've often seen 0.2 when we're talking about Cohen's recommendations, but 0.2, 0.3 effect size. Moderate, generally 0.5. Large, 0.7, although I've often seen 0.8. So I'm putting both of those in just so you see both. But I also want to stress that Cohen was very much against always using these as a rule. So he did suggest them as a general suggestion, but what he really wanted to say was, whenever you're conducting research or whenever you're reading research, you must judge the practical and statistical significance in the context in which the results are used. So you really need to take it on a case-by-case basis. And a lot of that just comes with experience in the field. In a specific field, you might say, wow, 0.8, that's really high. Where in other fields, like business or economics, 0.8 isn't always that high. Two types of inferential tests. One is using interval or ratio, so this continuous data. That would be a parametric test. If any of your variables are, I should add, parametric. And non-parametric would be when all of your variables are nominal or ordinal. Okay, and I clarified there because one of the most basic tests, a t-test, one of your variables is continuous. It's the outcome measure you're looking at. But your independent variable in a t-test is just which group you belong to, and that would be a category. So we have an independent samples, which means you have two separate groups. We might look at a group of students at UNF college versus UWF. Maybe we want to compare the two colleges. And we could get an average SAT score of incoming students at UNF and an average SAT score of students coming in at UWF. And this would allow us to compare some kind of selection standards between the two colleges. Dependent sample, on the other hand, we're going to either have the same person before and after on a different variable. So maybe before I take this class, after I take this class, we take a measurement in both cases. Or it might be if we can create a really good match, and this is hard to do, but if you can, so I put an example here, marital counseling. Maybe you have 50 couples that go through counseling, and so we somehow want that male and female data matched for each couple. You don't want to just take the mean of all the males and the mean of all the females, because you lose valuable information. We lose the fact that this particular male is married to this particular female. So if we can connect the data in that way, we can match using a dependent t-test. And either way, whether it's pre-post of the same person or partners, basically, it's conducted the same statistically. Now in ANOVA, you may have heard this word, is an extension of the t-test. T-test is really an ANOVA with two groups, but within ANOVA we could have more groups. We could add University of South Florida, we could add Ohio University, we could add all these different universities, as many as we want really, and then look at the mean SAT score of admitted students, and that would be an ANOVA test. And omnibus is the overall, is there a difference anywhere between any of the groups in the group means? Whereas then we would also have a post hoc test to see differences between specific means. Factorial ANOVA is when we're looking at two or more independent variables. So we might have gender and age, or we might have type of instruction and gender, or race, or SES status, assuming that SES status was put into categories. And in that case, we could be looking for main effect of any individual independent variable, or an interaction effect, so that we might say people in treatment 1, it was better for males, but wasn't effective for females. Treatment 2 was effective for females, but not males. So it depends which treatment you're in based on your gender. We'd say there'd be an interaction between gender and treatment. Okay, and then there's some more sophisticated tests that we won't get into as much in